Okay, we're going to take a look at those limit properties and verbalize them in English language. And we're going to use those properties to find limits graphically and algebraically. So here's our list of rules that you already had. But when we take a look at them, we kind of want to think about what do they mean in English. So this first one, the limit of k as x approaches c, well, k is just a constant horizontal line. And so as x approaches any value, you are always going to get the y value of the horizontal line. So the value is k. So the limit as x approaches c of a constant is the constant. The next one, the identity rule. I have a picture of it down here below for number 2. Here's the identity, y equals x. And remember, as x approaches c, well, the y value is c, since y equals x. So we're just going to say the limit of x is c. All right, the rest of them are a little more easy to verbalize in English. So the limit of a constant times a function is the same as the constant times the limit of the function. The sum rule, the limit of a sum is the sum of the limits. The difference rule, the limit of a difference is the difference of the limits. The product rule, the limit of a product is the product of the limits. The quotient rule, the limit of a quotient is the quotient of the limits, provided the denominator is not 0. And the power rule, the limit of a function raised to a power is the limit of the function raised to the power. Okay, so we're going to use those limit properties in just a bit. Taking a look at the definition, well, not the definition, but the limit statement, all right? The limit as x approaches c of the function f of x is the value L. All right, we care about x getting arbitrarily close to c, but not equal to c. Okay, we don't care about x being equal to c, we care about it getting close. Okay, so for example, if I have a function, right, and here's where c is, I care about x getting close to c, right, from either direction, and what the y value is getting close to. Okay? All right, in order for this limit to exist, the values of f must be the same or tend to the same number L as x approaches c from both the left and the right-hand side. Okay, so talking about this function, right, here's c, and we've got some y value. Right, as you approach c from the left, and as you approach c from the right, the y value is the same. Right, so we designate the left-hand limit by saying x approaches c from the left with a little negative sign above the c. All right, that indicates the left-hand limit. And we indicate the right-hand limit with a little positive sign. So as x approaches c from the right-hand side. All right, so this would be my right-hand side and my left-hand side. And the limit is approaching the same thing. Okay, so we could have a function that has a jump in it, in which case the limit from the right might be some y value here, and the limit from the left might be this different y value here. Right? These two limits are not going to be the same, so our limit will not exist. So we'll say does not exist. All right, let's take a look at some examples. Okay, so I've got the graph of the greatest integer function. Okay, the greatest integer function is this step function. Okay, it has, well, it is the greatest integer less than or equal to the number that you're inputting. So, first of all, some notation. It's written here, but it might be a little bit small to see. G of x is equal to, they use square brackets with the x inside, and sometimes those square brackets are double barred. Okay, so that's the greatest integer function. If I want the greatest integer less than or equal to 3.5, well, here's 3.5. The greatest integer less than or equal to 3.5 is 3. If I say, what's the greatest integer less than or equal to 2.7? Well, it's 2. What about a negative number? What's the greatest integer less than or equal to negative 1.3? 1.3 somewhere in here. The greatest integer less than or equal to 1.3 is negative 2. Okay, so let's take a look at some examples finding some limits. Okay, the limit of the greatest integer as x gets close to 0.6. All right, 0.6 is somewhere in here between 0 and 1. The greatest integer less than or equal to 0.6 is 0. What's the greatest integer less than or equal to negative 2.9? Negative 2.9, greatest integer less than or equal to that is negative 3. Okay, these next three questions, 3, 4, and 5, kind of go together. A little family of limits here. The first one we're taking a look at as x approaches negative 2 from the left on the greatest integer function. So from the left, as x approaches 2 from the left, we're going to get a y value of 1, the greatest integer. Right, so, that's 1.5, 1.7, 1.9. What's the greatest integer less than those numbers? 1. Okay, the limit of the greatest integer value as x approaches 2 from the right. So from the right, like 2.3, 2.2, 2.1. What's the greatest integer less than those values? 2. Okay, notice the left-hand limit and the right-hand limit are not the same, and therefore the limit as x approaches 2, we're going to say does not exist. We sometimes just abbreviate that DNE. All right, questions 6 through 10. Looking at this new graph. The limit as x approaches 3, here's 3, from the left and from the right, looks like we approach a y value of negative 1. The limit as x approaches 2. Now notice the function value to f of 2 is actually the point 2, 0. Okay, so there's the function value, but we don't care about what happens when x is 2. What we care about is what happens, what do our y values tend toward as x approaches 2. So as x approaches 2 from the right and from the left, the y value is negative 2, even though the function value is 0. All right, 8, 9, and 10 all go together. So the limit as x approaches 0 from the left. So we're approaching 0 from the left. Our y value is 1. Let's look at the function as we approach 0 from the right. The y value is 0. Notice the limit on the left and the limit on the right are not equal, so the limit as x approaches 0 does not exist. All right, these next 4 questions are asking us to use the properties of limits, so apply these ideas to these limit questions. So in this first question, we have the limit of a sum. Remember, the limit of a sum is the sum of the limits. So I'm going to say the limit of f of x plus the limit of 5 times g of x. As x approaches 2 in both instances. All right, that looks simple enough, but let's take a look at the limit of a constant times a function. The limit of a constant times a function is going to be the constant times the limit of the function. Okay. So what is the limit of f of x as x approaches 2? F of x is this roller coaster looking function here. Oh, I apologize. That's as x approaches negative 2. Negative 2. Okay, so as x approaches negative 2, my y value approaches positive 1. Even though my function value is 2, my y value approaches 1. So this is going to be 1 for this piece, the limit of f of x. What's 5 times the limit of g of x as x approaches negative 2? G of x as x approaches negative 2 is negative 1. So we're going to have plus 5 times negative 1. All right, 1 plus negative 5 is negative 4. Okay. Number 12, we have the limit of a product. The limit of the product is the product of the limits. Okay, here we're looking as x approaches 1. All right, the limit of f of x as x approaches 1 is 2. The limit of g of x as x approaches 1, well, on the right it approaches negative 1, on the left it approaches negative 2. This limit doesn't exist. So we're going to say that this limit of the product does not exist. Okay, number 13, the limit of a quotient is the same as the quotient of the limits. Okay, I should really have as x approaches 2 underneath here. So the limit of f of x as x approaches 2. Right, did I get that right? That's a 2, positive 2. So 1, 2. So why don't we call that 1.5? 1.5. And the limit of g of x as x approaches 2 is 0, which is unfortunate because I can't do that. So this limit does not exist. Or does it? No, it's not going to exist, right? Okay. I could say the limit exists from the right or from the left, but not from both directions. Okay. The limit of a function to a power is the same as the limit of the function raised to the power. Let's wrap this one up. The limit of g of x as x approaches 3, 1, 2, 3, is 1. And so we're looking at 1 squared, which is 1. Okay. We will continue in our next video with more limits graphically.